Am I audible now? Yeah. Okay. Thank you, Priyanka. And thank you, everybody, for having me here. It's my pleasure to be here for the first time. Okay. And so far has been very good experience. And when I entered this building, my first comment about this building to Priyanka was, this institute building looks like a home. So it is indeed very good home for all of you. And I'm pleased to be welcomed in your home. I will present this topic, which is based on one of my PhD students' work. She did finish in 2016 and 17. She did work in a very interesting topic because this was one of the first studies in Europe and first study in the UK, definitely, focusing on a particular aspect of resource recovery at full scale. Of course, this work was done by different groups at smaller scales, lab scales, pilot trials, but not really at full scale. So this was the first time full scale was tried in the UK. And the particular aspect of resource recovery from wastewater was focused on nutrients, phosphorus and nitrogen. Okay. So I will go through this study through first starting with the background of this topic and then explaining a particular case study in the UK. Okay. And I hope it's going to be interesting for you. If you feel like there is some topic which is not clear to you, perhaps after the presentation we can have a discussion and you can ask any questions. Okay. So from let's say regulation point of view, in the UK, rules of the European Union, they do get adopted. As most of you might know, that European Union has many countries as a member of states, and there is a central document that is published by European Union, and all these countries like UK or France or Netherlands, they adopt those documents into their country. Okay, so the main document is the same, but the way it is adopted in the individual countries could be different. For example, this table comes from this legal document, directive number is written there. It says that if you are discharging treated wastewater into a natural environment, for example, a river in this case, this is how you need to maintain the amount of nutrients, concentration of nutrients. Okay, so for example, total phosphorus has to be less than 2 milligrams per liter for large cities with population more than 100,000, less than 1 milligram per liter for smaller cities. Similarly for total nitrogen. Okay, when these regulations are adopted into individual countries, for example, in the UK, they too take there's a fundamental principle guides, and then they add subsequent rules and regulations beyond those. It does not mean they compromise these rules, they add additional rules on that, so as to adopt actually the local conditions of the country. So in the UK, there has been not much changes into this one, except that they also added not just total nitrogen, but also ammonium concentration separately, okay, so as additional control measure. And they also reclassified definition of cities. So they classify not just a large city more than 100,000 population and a small city less. They also added villages into it. Okay, so small villages will have more relaxed criteria because they are contributing to very smaller loads into a natural environment as compared to large cities. So with these type of regulatory requirements coming from European Framework Directive, the methodologies of wastewater treatment have been developed in the countries like UK. So this is the background why and how different wastewater treatment companies in the UK, they are driven to treat wastewater. Okay. Now, the current situation is somewhere in between these two diagrams. So let's say 20-30 years ago, diagram 1 was the most common scenario, which means even if all the cities and towns had wastewater treatment plants, many of them were poorly engineered, which means the wastewater which was going into the aquatic system was not up to very high quality. Okay, and the residual from wastewater treatment plants, they were mostly transported to landfills. I'm talking about 20-30 years ago. Okay, so basically the concerns of pollution were not completely addressed, because if you have some pollutants going still into the environment, you have pollution emission. And even if you are cleaning up this one, if you are transporting sludge into landfills, and if these landfills are not appropriately designed, they will further pollute the groundwater and so on. Okay. So now transition is up to this stage, advanced wastewater treatment processes. And in fact, in many places, very specific places in the UK, this ideal diagram, let's say, is still valid. As many of the cities, most common cities, are still struggling to achieve this sort of diagram, which means imagination of centralized treatment plants, which people still don't question in the UK for large cities. They still imagine large centralized treatment plants are the major infrastructure for wastewater treatment. People are free to build decentralized treatment system, but they will never replace the requirement of large treatment plants, even if pollution is reduced. And the vision behind is that it is going to release a very high quality water to the aquatic ecosystem so that its productivity is maintained. You don't just throw away sludge into landfills or similar places, but actually you process it further. You can recycle sludge directly because European regulation does allow recycling of sludge, as long as it is done in a way that it's not going to pollute environment and not going to contribute to the contamination accumulation in agricultural products. But at the same time, there is a drive towards recovering pure fertilizers rather than just sludge disposed into the agricultural lands. And then there is also emphasis on, if possible, you generate bioenergy from wastewater treatment while you are doing wastewater treatment, so that you can make this whole process energy neutral, if not energy positive. Okay, so this is what most of the large companies are trying to achieve. Not all of them are successful achieving everything, but all of them are doing at least one of these three things. Okay, so either they are doing bioenergy recovery, or they are doing fertilizer, or they are doing sludge recycling. In ideal condition, of course, they should be doing everything. Okay, so I will be presenting a case scenario in which a particular wastewater treatment plant we adapted through a PhD study. It was, of course, a particular company's endeavor. They were doing it, but we did a PhD study to guide through, to provide knowledge base, so that this transition from, let's say, old style treatment plants will go to the new style treatment plants in which you recover energy and useful materials such as fertilizers. Now, this idea of making sure that you recover all the resources, energy and materials from wastewater, if you look into the potential conceptual flow pathway of wastewater through different stages of treatment, we can think what are the research challenges into achieving this. Actually, in reality, scientific research challenges. So if this is wastewater, comes through different processes, you can have very let's say basic level of treatment in order to produce fairly cleaner water, but some energy. Okay, but that cleaner water probably will have very little potential for reuse. If you clean it a little bit further, you can produce very high quality water, but maybe you don't get any energy gain. Okay, so extracting small amount of energy is the easiest way of let's say encouraging wastewater treatment, but the effluent will be very poor quality. The moment you try to achieve high quality, that's where you start investing a lot of energy, and therefore it becomes burden actually, unless you value this water that comes out of it. So what are the, let's say, scientific challenges in doing all this? Challenges are, you look into the application of novel materials, novel physicochemical processes, so that you can actually, in principle, advance this to make, let's say, very dirty, from the very dirty water to drinking water. You apply novel chemical processes to capture all the elements you want. For example, nitrogen and phosphorus are very useful elements, and that can be used as a very important material. And then you look into novel application of microbiology in order to remove all carbon, nitrogen, phosphorus in most cost-effective way, because achieving everything chemically probably will be very expensive. Okay, so in reality, if you want to achieve the, sorry, what we discussed previously, this one, it will not be just by biological process or chemical process. Probably it will be a combination of many of these processes if to achieve an ideal scenario. Okay, I will now focus on phosphorus. I will not discuss on energy. There's a lot of work has been done. I can give you one impression is that recovering energy from wastewater is well established. You can find many ways to do it. The only thing which I would like to highlight, if you are studying energy recovery from wastewater, look into the maximum potential of energy you can recover first. because there is a limit how much energy is theoretically embedded into wastewater. Okay, and people have done enough research now to push that limit and achieve almost all of the energy that is present in wastewater. But still, there are different pathways to recover energy, perhaps worth studying. Now I'm more focusing on materials because these are something new ones. They can add value to the further resource recovery from wastewater. And one of the materials I will focus in this particular presentation is phosphorus. The way it is dealt in the treatment plants is like this. Either they remove chemically, which means they will add chemicals like iron chloride, and it will get just precipitated as iron phosphate. Iron phosphate is a very stable material, which means once it's goes into iron phosphate form, you cannot use this as a fertilizer. Plants cannot take it. You have to just dispose it somewhere. Okay, it's like a rock. Other way of removing treatment plants is biological phosphorus removal. If you do that, you will have phosphorus embedded into the cells of microorganisms, cells of bacteria, which is easy to take away. But obviously, what you do after that is a problem. Okay, but from phosphorus removal point of view, they are both working fine. Easy way of this was you don't need much technical expertise. You just dump chemicals, it works. Difficult part of this is that it needs a lot of expertise. If operators should know how to operate biological removal process. If they do little mistakes in operation, this process may fail. But obviously, it's very cost effective because it's a biological method. It requires no external chemicals. So in terms of, let's say, process diagrams, you have very basic wastewater treatment plants in just with one aeration tank. You can design it, but that is not going to remove your nutrients, nitrogen, phosphorus. You can design two-tank system. I'm talking about large centralized treatment plants, okay? And you can remove nitrogen and phosphorus. If you want to go for biological phosphorus removal, you have to go for multiple tank sort of system in which you cultivate a special type of microorganisms, and they are the ones which will remove the phosphorus from the system. Okay. Now that is from the wastewater treatment plant point of view. Now let's go one step back and see why phosphorus is important to be removed from wastewater and what else we could do with that. Looking into phosphorus, actually why it comes into the wastewater is because we eat a lot of food and food has phosphate in it. And why food has phosphate in it? Because this is embedded in vegetables, meat, and anything we eat. And this is building block of our lives or any lives. Okay, it's part of DNA. It's part of cellular structures. Okay, so way it enters into living organism is this way. In modern world, when we do intensive agriculture, we mine phosphorus from rocks. Okay, we produce them into form of chemical we call fertilizer, because then we can do intensive agriculture. Okay, we produce these foods and we eat it, and human feces will carry phosphate into the wastewater. Okay, looking back into where this phosphate actually comes from, for example, from India. Okay, if let's say farmers are using fertilizer, phosphate containing fertilizer, where does it come from? Anybody aware of that? Anybody having idea on where Indian phosphate comes from? We don't have phosphate in India. Not really. So you can do some research on this. You will realize that phosphorus is imported, and it's not just India. Major part of the world actually does not have phosphate. So these are three places which have majority, let's say more than 80–90% of phosphate in these three places. Okay. Of course, our nearest neighbor is this one. Probably is the easiest way to get it. But obviously, Morocco also has got many industries which process from North Africa and they sell it to Asian countries. Okay. So probably we are getting for many of these places or both. USA, like they're clever people, you know, they keep their things for us. First, let other people finish their part. Okay, but they have got a big reserve. Okay, so basically, if you want to sustain our food production, if you want to have food on our table, we have to be friends with these three people. Okay, at least one of them. Okay, and it is true for India, UK, or any other country, and particularly, let's say, from 20 years after today, is because these are rocks. One day they will finish like oil, okay, or they will diminish, and while they're diminishing, their prices might go high because of their needs. unless we invent new ways of producing food, unless we don't eat food, or we have very few people, okay, which are really likely scenario. Most likely scenario is that world population will be increasing and we will need more food. And if we need to produce more food, this is the only way to go, which is intensive agriculture. So basically, imagine the whole world, and you've got 3 rocks, big rocks, and these are coming different places, okay? Now, this phosphorus is listed in a category of critical raw materials. This is European Union definition. European Union, if you Google European Union critical raw materials, the list of certain minerals which are considered critical, which means if you block them, country's economy will be hampered. If you let them not flow into a certain economy, probably the economy will be quite volatile. And phosphorus comes under critical category. There are others which are not critical, which means you can get them from somewhere. What do you think about nitrogen? Urea comes from nitrogen. Okay. Is nitrogen a critical element? It's in the air, 70%, 80%. It's all nitrogen around us. It's just a matter of capturing it. Okay, it's not critical element. It is not cheap to just produce urea from nitrogen. That's why we pay a price for urea. But nitrogen as such is not a critical element because it's in the air, freely available so far. In scarcity. Yes, because for example, if you want to get phosphorus, you just can't travel around India and get it because it is not in India. So let's say look at historical sort of the way it is going from let's say recent history from last let's say 10-15 years. It goes up and down very quickly, and obviously what happens with all this phosphorus? Agriculture, let's say runoff, when you have excess use of fertilizer, some of them will just go away with rain, pollute the nature, pollute the aquatic environment, and large part of course human waste or animal waste, this will be carried into the aquatic environment if you don't remove it and create pollution, and that part of pollution we call eutrophication. Okay, so that's the journey of phosphorus. It starts from rocks and it ends up in aquatic bodies causing pollution, eutrophication. I have data only for the UK. I don't have anything for India. If people did calculate material balance, so 138 kiloton of phosphorus per year is imported in the UK. This is net import. It is less just because UK manufactures certain things which use phosphate and then sell it somewhere. That's how some part of phosphate goes out. But actually, all of the phosphorus, net phosphorus that comes from mainly here and probably here. Look into its consumption pattern. So in the different forms of phosphorus, so this part, blue part is the rock, you know, the one we mine from natural resources. Okay, so the consumption of rocks, you can see timeline. This is 1800, this is 2000, and this is World War. Okay, and this is peaceful time from here to here, and therefore we are having more and more people, more and more agriculture, more and more food, and we are continuously using more. So this is the global trend. Of course, we could have recycled more manure, okay, but we did not do this. There is very little, almost no increase in the manure phosphate recycling. So basically, whatever phosphate phosphorus we are using, we are just mining the rocks and we are using in agriculture production. Okay. And in terms of European definition of critical raw materials, so if this is economic importance on y-axis, and this is supply risk, this is where it is. So this box is considered risky. So its economic importance is quite high, and risk is just starting to be high as well. So in future, a phosphate might go like this. Okay. If you want to compare what happens globally, I will just show bigger consumers: Europe, China, India. So this is world, of course, which is increasing trend still. This is Europe. You see interesting trend. This is China. Okay, and India is red one. Look at the China and India recently. Okay, and look at European Union recently. Why do you think it's like that? Anybody can comment on that? Yes, yes, I think that's one of the reasons Europe is more and more buying food from outside. And second reason is that European agriculture is more sustainable in terms of fertilizer use. So they have developed technologies not to use excess fertilizer. Even if they're producing a lot of food, they try to protect their environment. So it's not because they are producing less food. They're not compromising their food production. It's just that they have developed technologies so that their farmers are not using more fertilizer than required. So for example, in China, if let's say 2 tons of phosphate is required, they will add 3 tons, just to be, safer side. It's just add a bit more. Like it will do something nice with it, at least it's not limiting. But thing is that extra 1 ton with rainwater will just flow into your aquatic body, and that's why you might have heard in Chinese news, a lot of their fresh bodies are dead because they are massive. They have their own phosphate. They don't care about the price of the phosphorus as such. But in Europe, even if price was not important, most of the Western European countries, for them, phosphate is still very cheap material they can buy from China or from Morocco. But they value their water resources. So they protect it not because they want to save money. They protect because the cost of pollution is very high that goes through agriculture runoff. Okay, so that is why in European Union, as science and technology progressed, there is less and less phosphorus consumption. Even if they are producing food, they are using a lot of phosphorus. They're not adding too much of phosphorus. They have implemented rules to reduce phosphorus, not only in agriculture, but also in production of other activities. For example, soap used to use a lot of phosphate in the past, let's say 40, 50 years ago. And they made rules that soap making industries cannot use phosphate, or they have to use below certain limits. And that's how they have controlled phosphate. Similarly, they are trying to address all the possible sources of phosphorus so that they protect the natural environment. It's not aimed at money saving, basically. Okay, now I'll show you the global scenario about how phosphorus moves globally. So let's say this is the rock that is mined. People mine the rocks. Typically, they dissolve into acid. They create what we call phosphoric acid, and that's what they sell. And many big companies who actually produce fertilizer, they buy not rocks, just phosphoric acid tankers, big tankers. They're shipped, and then they will produce the fertilizer or any product of their choice. Okay, so when this fertilizer is produced, it goes into the soil. The first thing that happens, big thing, is actually lost in the soil itself. Okay, so European Union had addressed this part. It's quite big part, actually. Imagine out of 15 tons, megatons per year, 8 just goes into just because you are throwing too much of fertilizer. Some of things you could control. Some of things, their processes are very complicated. I'm currently doing a new research on looking into processes which are involved in loss of phosphate during the agriculture, during crop growth. That is a different area of research. But I would say in European countries, they actually have covered half of this pretty much, because they have looked into how to dose systematically in only minimum required phosphate, so that it's not hampering the agriculture, at the same time not going as a waste material. And what comes next? There are lots of other losses. For example, losses through the food. You produce too much food and you left in the farm because it's not economically viable to harvest it anymore. It's too much. It happens in India as well, but it happens in other countries as well. Okay, so these are the just losses because you produce too much. It's not worth taking it out. And then you start doing other agriculture activities. For example, rearing animals. Okay, so through the manure and everything, you will lose. And then it comes to human part. Okay, when it becomes food. Food, vegetarian or non-vegetarian, anything that is grown based on the crop produced in agriculture, we will consume it, we will flush it, it will go to the environment. Okay, And this is how it is happening, which means a very precious material, a part of that is flushed, part of that goes into soil, part of that is lost as excreta of the animals. Okay, now I'm going to focus very quickly on this part only. Okay, human part, wastewater treatment plant. Now this is useful material and goes in wastewater treatment plant, and what it does inside. Let's say you design large scale wastewater treatment plant. There are more things that happen because of phosphorus. These are recently discovered from last 10-15 years. Actually, the utility operators, they figured out, actually it's not just the loss of phosphorus and its pollution into environment. If phosphorus moves through your pipes, because of other cations present in your water, in wastewater, which is ammonium and magnesium, it can naturally form, especially when pH is appropriate, a material called struvite. It's magnesium ammonium phosphate times 6H2O. This material is quite nice and stable. It's very good if you feed plants, okay, this material, because it's nice fertilizer. But it's not nice thing if it's deposited in your pipes. What will happen? The diameter of your pipe will slowly start decreasing. Okay, so what happens to the flow velocity? It increases. Well, and then you can imagine the problem in the whole pipe infrastructure. In the UK, manpower is very expensive. Anything breaks down is not a loss of pipe. They don't care about price of pipe. It's very cheap. But the guy who comes to repair it will show a lot of busy appointments. He'll not come in 2 days and come in 3 days, and then we'll be spending 2 days just trying to look into what's happening and charge a lot of money based on per hour. Okay, so it's a really big challenge for water companies. This very precious material, which they could have used it, actually depositing here, destroying their pipes. It actually deteriorates infrastructure continuously. So water companies, when they started doing phosphorus research on treatment plants, actually their first concern was not at all about value of phosphorus. They did not care about value because it's not their area of research. They just were worried about their infrastructure, the costly infrastructure which they have put in place. So they just came to us saying that I don't want this deposited in my pipes. That's all. It goes anywhere else, not in the pipes. Okay. So that was the first concern, because pipe diameter decreased, energy consumption in the whole system because of pumping increased, maintenance cost increased. So the concept what we suggest to them is you look into the point source, which means where the phosphorus comes in the system. Okay, so basically when they have biological phosphorus removal system, phosphorus goes into bacterial cells. Okay, so in your biological sludge you have got phosphate. So from sludge pipes, when they do sludge treatment and they do recycle of sludge back to the inlet, pipes are problematic in only those areas because they have got very high phosphate concentration in those. So we suggest that if you capture the phosphate right in the sludge, exactly from there, you remove most of the phosphorus from the system completely. And while you are removing, why don't you let this precipitate in a controlled environment rather than your pipes? If you let it precipitate in controlled environment, you just collect this material and sell it as a fertilizer. Okay, this is the easiest part because this is very naturally precipitating material in those conditions in treatment plants. Okay, you can make many materials out of phosphate and maybe all of them are good fertilizers. Okay, but this one was very easy to apply into the treatment plant. That's why we tested on this, and many countries in USA, Canada, and many places, they are using this material as a fertilizer which can be recovered in the wastewater treatment plants. Okay, but we are doing research on many other options, many other types of good fertilizers which can be recovered. This is one of the best fertilizers, by the way, if you want to go for this one. Okay, so what will be the impact if you apply this, let's say on a country scale, on a large city scale? What will be the impact of this one? Basically, the current cycle is this: you're mining phosphate rocks, you're using in agriculture, producing food, it goes to the wastewater treatment plants, it goes to pollute environment. This is going to just cause aquatic environmental degradation, basically. Okay, and not only that, from fertilizer you also have some runoff. It creates the same problem. Okay, so if you apply phosphorus recovery here, you basically break this and you can make this kind of circle. Okay, so if you create this closed loop, basically just by focusing phosphorus, you can have a lot of benefits. First, you're protecting your environment. You're protecting consumption, because if you have feed from this side, you need less of this side. You're sustaining agriculture, and basically this will create an economy of its own. Okay, so for future, what we envision is that if you recycle phosphate back into here, a big problem of the aquatic environment pollution could be handled. Okay, if not all. Okay, of course, parallel research has to be done on the soil erosion side and manure side. Manure one is very similar to human waste. You can do the same thing with the manure as well. And soil erosion is different topic, needs to be addressed separately. Okay, so if you apply this concept of steroid material recovery, you will have basically reduced steroid precipitation into your pipes. Your pipe will be, your infrastructure will be lasting long. You need less chemical to remove chemical, phosphate chemical means, because you have to remove phosphorus because of legal requirements anyway. You need less energy and maintenance because your system is running efficiently. You reduce phosphorus load in the system, and you can create revenue from the fertilizer. Okay. So we did scenarios analysis. So through the data that we obtained, which I'm going to show you some of the glimpse of that experimental investigation, our projection that my student did based on the data, if let's say this technology is installed into all large cities, big cities where you have central treatment plants, you could actually meet 40% of the domestic demand, which means you have to buy less phosphate only by applying this into the large cities. Okay, you can create industry of local fertilizer production, which means it might also reduce the cost related to transport of fertilizers from other continents. If you have to produce locally, produce small factories and send this to local farms, basically it's shortcutting. And this fertilizer, when we tested and compared with other fertilizers which are actually sold in the market, is better for farmers to control, because it releases the phosphate in soil slowly because of its nature. The compounds that you buy from market, you put it with little water, it leaches very fast. Why people invented that way, if you question them. Actually, they invented that way many years ago because they wanted to see immediate results. You throw the phosphate, you want to see the plant growing quickly, and then they have 2 rains and then you have to feed it again. Okay, but if we use these fertilizers, and now the factories, the fertilizer making industry is also making equivalent slow release fertilizers as well. In the UK, in Germany, in France, it's very common that you can buy slow release fertilizer these days for your gardens and everything. And it will be much more cost effective because you need a smaller dose and it will release phosphorus slowly. Okay, and therefore it will last longer, it will clear less pollution. So this by default is slow. By luck, this is a slow release fertilizer. Therefore, you need less in quantity if you are feeding into agriculture. And therefore, if globally it is applied, you have less reliance on naturally occurring phosphate mines into these 3 countries. Okay. So this is the case study I'd like to show you very quickly. Okay. Before we go to that case study, I'd like to show you video, because video was made and my student who finished PhD is also in there in that video. Then you know the sites exactly, where exactly the site, how it looks like. Then I'll show you the data further.
On Rowley Farm just outside Slough. The 200 Jersey cows here are fed on grass and oats grown on site. There's about 200 acres of farmland here.
We grow grass for the cows and maize, and then we grow arable crops like wheat.
Farmer John Whitby uses a range of fertilizers, nitrates, potassium, phosphorus. Fertilizers partly responsible for the huge increase in crop yields.
Is it the maximum volume for the sound? Control? No. No.
Yeah, it's going on.
Okay, okay. Okay, thank you.
Path on Rowley Farm just outside Slough. The 200 Jersey cows here are fed on grass and oats grown on site. There's about 200 acres of farmland here.
We grow grass for the cows and maize, and then we grow arable crops like wheat.
Farmer John Whitby uses a range of fertilizers, nitrates, potassium, phosphorus. Fertilizers partly responsible for the huge increase in crop yields seen in the 20th century.
Yes, crops will grow without fertilizer, but they won't be as productive.
Farmers across the world will use fertilizers, much of it phosphate-based, but phosphorus, rather like oil, is a finite resource, and it's running out. Experts estimate phosphorus taken from mines could completely run out in less than 100 years.
I think the implications are lower crop yields, less food for the world, and that is serious given a growing population.
Yeah, it is that serious.
Just that fundamental, yes.
So, is this the solution? It is frankly a little unpalatable, but part of the answer may lie in human excrement.
When I look at this, I think this is probably the most disgusting thing I've ever seen.
I think you need to look at things in a better way than you do now. So you see it as a resource.
You see it as a resource?
Yeah.
This is Thames Water's sewage treatment works in Slough. The waste here is rich in nutrients like ammonia and phosphorus, so much so it creates quite a problem, clogging up the miles and miles of pipes. Thames Water used to spend hundreds of thousands of pounds a year cleaning out their pipes, but now they've found a new use for the phosphorus deposit.
The solution is to make a phosphorus fertilizer. So using the same stuff that fills up the pipes, we can put that through a reactor and make a fertilizer instead. So we've used something that's usually a pollutant and a nuisance as a resource.
The reactor officially opens today and is the first in Europe. Wastewater is refined and crystallized. The result, high-grade fertilizer. They'll only produce 150 tons a year here, a drop in the ocean. Farmers used 140,000 tons of phosphate-based fertilizer last year in the UK, but it's a start.
In order to sustain life on the planet, we have to be smart about the resources that we use. And nutrients is just another one of those areas that provides us with an opportunity to recover a resource that's precious and that can be very important down the road as we grow and need to feed more and more people.
Back on the farm, John knows all about recycling. He uses manure from his dairy herd to enrich his land. The experts now want us to see human excrement not as waste, but as a valuable resource.
Okay, so the video is show. It is the site that I'm going to discuss. The data which I'm going to, the study which I'm going to present belong to that particular site. And when the recovered fertilizer, this is the construction phase when this phosphate recovery system was being built. And this is the pellet that is actually the fertilizer. And Priyanka has got some sample, you can have a look at it. So why this pellet? Why this? Because it has size exactly same as the one they buy in the market, okay? So their hopper and distribution system, they don't have to alter. They can feed exactly the same sort of machinery and everything. But instead of using chemical fertilizer, they can use this one, okay? So the site where this idea was tested at commercial scale. Commercial scale means the fertilizer which is being produced is being bought by farmers nearby, and they are using it. This is the process flow diagram of that particular treatment plant, which means it has got preliminary treatment, primary treatment, and then activated sludge process in which you have enhanced biological phosphorus removal system, which means it has got anaerobic chamber, anoxic chamber, aerobic chamber. And that system basically is called BNR system, which will enhance the phosphorus accumulating organism population, which means they will eat more and more of phosphate accumulate into the cells. And in this sludge, you will have, of course, a large population of those microorganisms. And if you crush those bacterial sludge into an anaerobic digester, the effluent of an anaerobic digester will have high concentration of phosphate. And this is the time when you can recover it, because only at high concentration of phosphate, the chemical precipitation of waste white is economically feasible. Okay, you can, if you try here, it won't work, because you will have very small suspension of these waste white particles and you will not be able to capture them. Okay, so you need a high concentration, roughly about more than 200 milligrams per liter of phosphate concentration, in order to be able to produce industrial scale fertilizer. This concentration is less than 20 milligrams per liter. Okay, so you have to concentrate 10 times, and this is how you can do it. You can do biological phosphorus uptake, take the sludge with phosphate rich accumulating rich bacteria, do anaerobic digestion, and recover fertilizer. Okay, this is the layout of the biological process that encourages phosphate accumulating organism growth: anaerobic, anoxic, aerobic, and then sedimentation time. Okay, this is the complete layout of that particular treatment plant. This is mass balance around that particular treatment plant, located in a place called Slough, just near London city. And after anaerobic digestion, this is the amount that we thought we will recover, and that was the initially predicted. This is a technology from Ostara Limited. It's a Canadian company. I can only show this diagram because this is publicly available, and furthermore, it's their classified information. So basically, when this work was started, before this installation of this system, the company was struggling with these matters. They were struggling with this chemical that is required for phosphate removal, because they have to remove phosphorus because of legal requirements. So they were doing iron addition because their biological system was not working properly. So first challenge was that how to make biological processes work. Because if you do not have technical competence, or if you don't take care of biological process, your biological system will collapse. And the easy fix is just add chemicals. But this is basically a vicious cycle. If you add chemicals, you destroy biological process. Then there is very little chance to recover that. Okay. So what we suggested first is to restore their biological process as it was designed, and then apply nutrient recovery system. So the way we suggested to restore their system is that we suggested to look into the microbial population performance. So you collect the biologically active sludge, run through this two-step test, what we call in 4 hours test. So in 2 hours you do anaerobic, which means you do just mixing, no aeration in the sludge, in a controlled reactor. So this is the bacterial sludge taken from plant, brought into laboratory, put into the reactor in aerobic condition, then aerated for another 2 hours. So in anaerobic phase, you expect that phosphate in the bacterial sludge will come out in the liquid. In aerobic phase, you suspect that if those bacteria are alive, they will uptake that phosphorus and consume in the cell. Okay, so this is what happens in a plant. If this diagram you don't obtain, it means your system is not working. So it's very easy to monitor. What they have to do is just 4-hour test. If they get this kind of curve, it means they have got bacteria which remove phosphate. If not, it means their chemical is the only thing that they are managing their plants on, which is not most sustainable approach of drilling with plants. So this is how the laboratory system is operated: 2 hours of anaerobic and 2 hours of aerobic phase, and first the preparation phase. Okay, so basically when we looked into continuously at certain period how this will evolve, we asked them to first not dose iron at all, we stop chemical removal, just rely on biological removal of phosphorus. Okay, and that's how it happened. It happened during the period of almost 1 year to adapt the whole wastewater treatment plant. So basically we monitor what we call a specific phosphorus release, the first 2 hour test, and we monitored a specific phosphorus uptake. So by the end of this April 2014, we restored the process. So a specific P release and uptake were higher than certain amount, which means that the net uptake is much higher than net release, which means bacteria are alive and they are eating phosphate rapidly, which means biological removal process is effective and working, and they don't need to add chemicals anymore. So this is the first stage of preparing any of the wastewater treatment plant that is basically meant for removing phosphate biologically. Only after this stage that you can actually think of recovering the phosphate. Okay, so we studied first what happened in terms of microbiology, how all this evolution of the processes took place during this period when we restored the microbiology of the old treatment plant. And it was very informative because it gave lots of details on what type of microorganisms actually were present in each cases. And we studied what sort of microorganisms are actually responsible for sustaining the health of biological phosphorus removal. Okay, so without going to their Latin names, you can just think that this is the type of organisms that when their growth is present, you know that your microbial system is healthy and is suitable for biological phosphorus removal. Okay, this is a problematic zone because there was a technician who came, he panicked, he added chemical. Okay, so this is how it happens in reality. So you are doing a long day of test and everything is working fine. And then one technician makes a decision that who is this doing all these tests? You know, I'm worried if it's not working fine, because if you add chemicals, normally it looks fine. So he just dumped a lot of iron chloride. So basically, we had to stop that event. And again, system recovered very quickly because there were enough population of the good population of microorganisms through the period. There was no chemical addition. Did I do something wrong? Okay. Okay. So basically, what we suggest in this case is that, okay, it is good in terms of if you have justification for the installation cost of the infrastructure for precipitating Wastewater or similar chemicals to compounds to recover phosphate as a fertilizer. If you have energy supply to run those machineries, it looks all fine. But what if you have problem with energy? What if you cannot afford those sophisticated infrastructure for making nice pellets of Wastewater? What you can do? So this is where we are doing at the moment work now. I have a project in Philippines, and it is the first time in Philippines we are trying to look into how we can avoid these energy intensive systems. So instead of making those fancy pellets, can we live with the powder, for example, you know, less complicated structure that we can produce in a lower cost. We can produce using lower energy, but gives is in a sense same amount of material as recovered. Okay, so we are trying to adapt this into low energy, low cost sort of environment. Or we are also looking into other simpler forms of pellets. You know, you don't have to make perfectly round ideal pellet. You know, you can go for some cheaper version of this one. So this is a project you can Google it. You will find some of the details. We are trying to look into Metro Manila, Philippines. Unfortunately, I never got a chance to try this in India. Nobody has invited me to try this in India, or maybe I didn't have time to explore too much where in India we could try this one. But I give you this idea. Maybe you can try one day somewhere to look into how to recover phosphate in a form that can be used in agriculture. India is probably the largest population country by now, if not officially. And obviously it's going to be one of the countries which will require largest amount of food in 10-20 years. This is the topic which is not just relevant to wastewater treatment. It's relevant to global food security. It's relevant to environmental protection in terms of protection of aquatic environment, sustainability of agriculture, and obviously wastewater treatment. Okay. Through this study, we have got idea that if you try to implement this in any treatment systems, don't try to add this in combination with chemicals. You might end up with a bad experience. The addition of chemicals basically causes alteration to the population of organisms. So you cannot just add chemicals and assume biological process will still work healthy. Okay. So if you are adding iron removal, chemical removal of phosphorus, just stick with chemical. Forget about biological. If you are designing biological process of removal, don't interfere with the chemicals. Okay. Obviously, you will prefer the second one because that's more sustainable. You don't need to buy chemicals. You don't need to release iron into the environment. But obviously, that has to be carefully designed and operated. Okay. The chemical addition will have negative effect on organisms which actually uptake phosphate into their cells, and therefore you will have not a good results in terms of phosphorus removal if you feed chemicals into it. So the idea of interaction of chemicals with useful biological species is very important and useful if you are planning a realistic, a real type of system design for phosphorus uptake and further recovery. Okay. These are the references. Main reference is a PhD thesis of my students. He finished and it's available online. If you Google, you get whole PhD thesis. And of course, all the details of the results and everything is in there. Okay. So I will close my talk on this point. If you have any questions, I will be happy to respond.
Thank you, Dr. Saroj. And now the floor is open for questions and answers.
Thank you, Saroj. I mean, I didn't know much about phosphate, and this seems like a very relevant topic, and it's a very good presentation. I had two questions. Firstly, I think just out of curiosity, I wanted to know in UK, what is driving these companies to make systems which are better than what they had in the past? Is it policy driven or is it something else? And the second question is, I can clearly see an application or the use of this recovery process in India, but given that our sewage system carry a lot of industrial waste and all of that, how is it possible for this idea to be adapted into an Indian context?
Okay, thank you. To answer the first one, I was highlighting actually the starting point of interest of private, especially in England, it's private sector. It's not government sector. It's entirely was the job of that private company if they wanted to do this or not. Okay, they chose to do it. The primary reason was the money. So surprisingly, it is an economically beneficial matter. They were losing the infrastructure. So the first they started with that they don't want damage on their infrastructure because infrastructure cost is very high there. And infrastructure damage was happening because of phosphate byproduct precipitation, which is a useful thing, but if it precipitates in pipe, it basically destroys their infrastructure. So that was the starting point. When they started, they thought, okay, we are doing it anyway, let's do in a certain way that policymakers are also happy. Okay, so basically they will combine their own interest with policy making. They got subsidy from government on this fertilizer. Okay, so their business spin-off, who is between the farmers and the wastewater company, they got subsidy. Basically, they can sell this fertilizer without taxation. So there is a new type of industry that evolved around this one. So yes, it is policy driven because otherwise they wouldn't go and run for subsidy. They wouldn't look into what are the government offers, and also they wouldn't advertise in such a massive manner. So they did influence themselves by policies, but their primary drive was mainly the economics. So if this has to run through, probably if it has to sustain, probably economy will be the first thing to do assessment. What is the economic drive that would work? So when I started this idea in Philippines, when I spoke with people, and interestingly enough, even if Philippines is a developing country, Metro Manila is managed by 2 large private companies. Okay, and one of the private companies is a partner in my project, and they did show interest as well because they said it's very difficult for them to buy that costly infrastructure, build it and run with that electricity. But if they can adapt it to the local condition, even if it's not producing nice pellets, it's just producing powders or some safe form, they will be more than happy because then they can say, okay, we have something to sell as well. And at the same time, we have guarantee of phosphate removal. In their regulation, this is 2018, their government has first time in history imposed regulation on phosphate, which they knew, of course, 2-3 years ago, that's going to be happening one day. So basically for them also, it is a matter of achieving things cost effectively. They have to remove phosphorus anyway. Why not remove in a way that it's good from policy and government point of view, at the same time, it is best for the money, basically. Now, in second part, when you say that in India or many places, when you have many things in wastewater, and even industrial products. And even from homes, you have these days you've got many studies saying that you have pharmaceutical origin compounds, you might have many other complicated compounds coming into the sewage. How safe is this? Now, it depends on which fertilizer you want to produce. If you want to produce this one, steroid, you know its chemistry, you know how it forms. Okay, it's very clear chemical process. Okay, you create a condition in which this compound forms. It's very unlikely you will have impurities in this one. It's very pure. We have done some material analysis, everything. It's one of the cleanest fertilizer actually, is because you create those redox condition in which you create this particular chemical. Now, problem is, of course, that other problematic things will still be there to deal with, but they will not appear in the fertilizer. They will be in the let's say leftover waste. And perhaps if you recover this and make some revenue from this, you have leverage of money to deal with other problematic compounds. Okay, those problematic compounds have to be dealt with, whether they are coming from industry or homes, doesn't matter. They have to deal with the wastewater treatment in any case, but this process will not treat them or will not carry them with the fertilizer. But again, it depends on if you want to create some other type of fertilizer. For example, you know that in many places, even in India, sludge cake from municipal wastewater is sold or is given to farmers. Okay, so if you dig the sludge, obviously you will have all of them, all of the things in there. If you have heavy metals, they will be there. If you have industrial waste, the traces of them will be there. So when you are looking at the sludge reuse in agriculture, so let's say this heap of sludge has got this much of fertilizer, but of course you can't pick that out. You just dispose that whole sludge into the farm, whole sludge cake into the farm. In that case, you are throwing all the problems in the farm. Okay, that's why in the EU there is a regulation on how much amount kilogram per hectare of sludge you can reuse, because they are worried if they allow too much of sludge usage in agriculture. Of course, farmer-borne nitrogen and phosphorus from sludge, but what if there is too much heavy metal also coming in? Because there are other problematic compounds that are coming. So that's why they have rules, a broad rule saying a certain kilograms per hectare is allowable. If you are a farmer, you're not allowed to use more than this these tons of sludge per hectare. It's because it's whole sludge you are throwing. But when you are using this one, then obviously is what you are extracting exactly the nitrogen and phosphorus and magnesium that you need for your farm. So you don't have to worry about that. But from treatment point of view, of course, wastewater has to be treated.
It was a nice talk, Dr. Saroj.
Yep.
I just had a quick question. I'm following up on Durba's question and what you explained. I mean, how feasible do you think? I mean, I know phosphorus is probably economically much more lucrative to sell, but you know, even nitrogenous fertilizers, they cost money to make when you are trying to fix it using Haber process or some other stuff.
Yeah.
So, how feasible is you know, getting the heavy loads of nitrogenous nitrates or things in sludge? Since you have worked in this field for years now, how feasible is maybe taking nitrates out, or you are taking phosphates out, which is as too white. So what about nitrogen, or you know, even potassium or the other stuff that are possibly very much in there in the sludge?
Yep. Okay. There is gold in human feces. You know that? Yeah. Okay. Now, you may not find that cost effective or feasible economically. If you start picking a gold from human feces, maybe from whole Bangalore shit, you can extract one earrings in few years. Okay. It's not economic. It's amusing. It's interesting. Nobody might buy your that particular jewelry, but it is theoretically possible. There is everything in wastewater that you can imagine, pretty much, but the concentrations are amazingly different. Luckily, nitrogen is in very high quantity, because you know we are eating food and nitrogen is very high quantity. The only reason nitrogen is not very much focused is because nitrogen's abundance. Okay, and the form of nitrogen that you've got in your sewage. When we recover sludge, the phosphate from our process, basically at this stage after anaerobic digestion, okay, after anaerobic digestion, you have got plenty of ammonium, lot of ammonium, and lot of phosphate, and bit of magnesium addition will create a steroid precipitation. Okay. Now, basically in steroid you are recovering nitrogen as well. Why we don't highlight nitrogen is because that's not major part of nitrogen. Major part of nitrogen has been eliminated here already, and not in a very useful form. It has been just thrown out in the air here. Okay, so in this here you have got denitrification happening, which means nitrogen gas bubbles out. So all the nitrogen that comes in, a large part of that will transform and goes as a nitrogen gas. Only the part that goes into bacterial cell, that will be recovered in the sludge and used in steroid. Okay, so large part of nitrogen in this recovery process is not recovered. It's only the part which is important to combine phosphate, because steroid is ammonium, magnesium phosphate. Yes, so basically you don't have nitrogen pollution here. You have very low total nitrogen because you can skip them as a nitrogen gas. Some people are always arguing that how to actually take out nitrogen, but because of the low value of nitrogen as an element, because it's all over, people find it's best way to just get rid of nitrogen. Okay, because otherwise it will create nitrate, and nitrate is a big pollution. You know, it's better to get rid of from liquid and put in the air than doing anything else. So that's the common understanding. If you want to see the importance of that nitrogen, people will argue that actually that small amount of nitrogen is very low value. Okay, if you see fertilizer making factories, the kind of scale they work in, they suck massive amount of nitrogen from air. Okay, and they then produce liquid and they produce urea from there. Okay, as compared to that amount, it's basically because it's such a low amount, there is very little economic benefit in it. So easiest way for treatment, point of view, is to just convert them into nitrogen gas.
Saroj, you know, some decades back, I remember in Delhi for our gardens, we recommended something called Okle ka khad, and it was basically very black in color, and it used to come from the Okla sewage treatment plant.
Yeah.
And it was considered as a very good thing for gardens and so on. So was that just sludge,
yes.
Right sludge,
yes.
dewatered sludge?
Yes.
So it would probably, at that time, maybe didn't have as many nasty things, other nasty things like it would be now. So it was, I think, reasonably safe to use in gardens and nurseries and
it depends how much you use. For example, exactly the reason why European regulation is the quantity limit is because if you start using in excess quantity, let's say if you've got a flower pot, okay, if you replace 50% of the materials with that sludge, it's problem. But if you replace 10% of that, probably it's okay, because
the Mali would know how much to mix and
yeah.
So if somebody knows gardening and all that, they would probably know that proportion. But my question is whether earlier this type of dewatered sludge was more safer because it was mostly just sewage, domestic sewage or whatever. But now with all the other emergent chemicals and plus industrial and other things, is it, you think that it's less safe to use the dewatered sludge?
Yes, it is. It has changed. But of course, what your statement is valid only in the places where there has been industrial growth. Okay, in villages it is still safe. If you're talking about small towns, small villages where there is a very little factory, just domestic sewage, sludge cake is still very safe thing to use in agriculture. There is no problem. It's only in the big cities, especially in the places where you have industrial domestic mixed. That's where you should be very careful about sludge cake usage. You know, if it's dry or semi-dry or whatever format it is. Sludge cake usage in those places is always should be subject to analysis. You need a proper sludge analysis, because sludge from one plant will be nowhere similar to sludge from other plant. They can be massively different because they bring very different type of amounts. So for every treatment plant, you need to analyze the sludge and look into if there is something very problematic. If it is the case, then it's better not to utilize the sludge at all. But from my understanding, in small places, especially those who are not, which are not industrialized places, normally sludge cake is very safe, and there are no problems, particularly dried sludge, you know, because what they do stabilization. It means they use calcium, you know, tuna, calcium hydroxide, and that kills any pathogens, any bacteria, viruses, and that's only recovery. Once you stabilize that, basically it's fine, you know, you can put into anywhere. There's nothing wrong with that.
What is the minimum scale of a sewage treatment plant needed for this to be economically viable? This sort of phosphate recovery.
Yeah, I think it's a very good question. The company who sells this technology, they say that minimum, let's say, about 100,000 population equivalent. Okay, 1 lakh people, city, a village, town, whatever you call it. Okay, if it is for less than 1 lakh people, 100,000 people, the whole economics might not work out. Okay, but theoretically speaking, if you want to run in your campus, probably it is feasible. They have done calculation based on their technology, the way they sell, the size of reactors they sell. Okay, these people who sell these type of reactors, they manufacture reactors, they're not gonna manufacture tailor wise. It's gonna be very expensive. They have got, and they will say which one you want, you know, just pick. And the lowest size they have got is like that. If you have very low population, low equivalent treatment plant size, probably the whole system is not ready for you. You might have to manufacture from scratch everything, or tailor-made sort of system, and in that case, it might become more expensive. But if you want to adapt the whole idea, like I'm trying in Philippines, not buying the commercially, you know, big energy-intensive reactor, rather fabricate very small reactor. You can operate any size. You know, you can operate for a hostel, you can operate for a house. It's entirely up to you.
Okay, and this was a biological treatment system.
It's municipal treatment plant, normal municipal treatment plant, the one you saw in the video.
The case study one,
yes.
Was it chemical or was it
biological?
Biological.
Yes.
In case of chemically done treatment plants, how common is this?
So basically, municipal wastewater treatment plants, they're not purely chemical, any of them, because it's not feasible to build chemical treatment plant for municipality. Normally, they are either just biological or combination. Okay. So what I was suggesting that you don't try to design combination. Okay. Just design purely biological. If you develop and provide the training to the people who operate it, you do not have to rely on chemical methods. You can operate biological methods. Biological methods are cheaper, but people need to know what they're doing. Okay, chemical methods are expensive, but a stupid person can also operate it. You know, it's just switch on, switch off reactors. Okay, so it's very easy to operate. Anybody can do it. So manpower wise, very cheap. You can do by remote if you want as well. But it's harmful and not cheap. Harmful because you, for example, if you're using alum, you release aluminum into environment. If you use iron, you have to deal with iron chemical sludge and so on. But if you use biological method, you're not using any metals into the system. But then you need to have person who knows that it's bacteria you are growing. You have to be delicate with that. Yeah.
In India, if a lot of the systems, these treatment systems receive mixed waste water, like they have industrial waste and sewage.
Yeah.
And if you suggest that we have a biological system, how do we then treat the industrial waste, which is also combined to the water? I mean,
so you do pre-treatment or post-treatment for industrial part. So, for example, there are many ways to do post-treatment. I'm doing that research on mixed wastewater. It's very interesting because it depends on industry. You know, if you have petrochemical mix, it's entirely different problem. If you have dye mixing, it's entirely different problem. But in most cases, if you do pre-treatment or post-treatment, you can deal with industrial constituents. So what I'm saying is that your main biological treatment, which addresses the main constituent of municipal treatment and some constituents of industry, depends on what industries. For example, if it's coming from brewery and winery, you know, I don't consider them like, you know, dyes or others, because they are like food products pretty much. They just increase a lot of load, but actually they are like pretty much. You don't have to design any chemical process for that. But if it is a dye factory effluent, pharmaceutical factory effluent, if it is coming from tanneries, if it's coming from a very complicated industry, then you need, and it's getting mixed into domestic, you have to have either post or pre-treatment to deal with it. These designs probably will not address exactly problematic part of that. They will remove, but not exactly the problematic part, because they are not able to remove the recalcitrant compounds.
I just wanted to make a small comment here in response to the Buzz question. A lot of the problems that industrial waste introduces actually can be solved by composting sludge. I mean, sludge composting has been followed in a lot of countries. We have problems of antibiotics, lots of endocrine disruptors, which they call these days, a lot of detergents. Some of them, if you treat you can actually control with composting if you keep an eye on the inoculant that you are using.
So are you talking about industrial wastewater?
Yeah, especially in places where you have mixing.
Mixed. Okay.
Yeah, the best of course would be to segregate. I mean, but segregation is something we, at least in countries like India, we haven't learned it very well. And it's especially easy to do with wastewater. Just let it out somewhere and be done with it. And I'm sure Bangalore's lakes are a testimony to that. So yeah, even with mixed up sludge, I mean, you can actually do multiple treatments with different inoculants and control the composting. But yeah, those need to be tested out. Depending on, as you said, what the industrial effluents are contributing.
So I understand what you are saying. Basically, this is the sludge that we are taking, doing treatment. For example, in our case, we are doing anaerobic digestion to recover energy, and then they're using the slurry to recover phosphate, and let other part go in the sludge cake, and dispose separately. What you are saying that's a separate sludge, which has got maybe a lot of industrial constituents. You can do further treatment using microbial populations and slowly degrade them. Composting or different type of biodegradation. I think it is possible. Only thing about what I suggest, when you are dealing with final residue, probably which has no value in it, let's say you've recovered phosphate or any other things, and now it's final residue, and it has got industrial constituents in it, okay, and they are very bad. Whatever you do, you have to make sure that you have done proper risk analysis. Okay, risk of failure understanding is very important. Very often I have done consultancy and I have not suggested any composting, any sort of slow processes. I define them. It's because slow processes give a chance for risk spread. Okay, and I suggest them 1 hour mycelia incineration, 1 hour blast of ozonation. Such a thing which solve problem in 10 minutes or 15 minutes. Basically, because for many places, for example, in the UK it works because for them, they cannot afford to have risk involved, because if that is caught by government, it's going to be a very big deal for them. Okay, so for them, they don't intend to do, let's say, adventure on learning composting. Yeah.
What take care of each component?
Definitely. I mean, biological processes are going to be always cheaper than the physicochemical ones. Definitely. Yeah.
Maybe I'll ask the last
Yeah.
question. So I think everybody over there is aware of eco-toilets. So where the urine and feces get separated at the schools itself.
Yes.
Right? And there has been a lot of newspaper reporting and all where toilets if urine is dried directly, it can produce this material which is maybe I'm just mispronouncing.
Yeah.
So my question is what do you think about this? Is it correct? And can this be scaled up?
Yeah, I think your idea is good because it has been tested. I can tell you that especially urine's idea has been tested in some developing countries, including Nepal actually, and some African countries. People have tested on urine because it's easiest to do it. Urine is purely liquid, and it has no microbial pollution. There is nothing. It's safe to deal with, and it has a balance of ammonium and phosphorus. So it's very good to do. So let's say if you've got a bucket of urine, you will get little bit of phosphate at the bottom. Okay, so it's just process managing how you deal with that processes. But good thing is that once you precipitate things, water looks very clean. So basically, it is very easy to implement on urine. Problem is the human feces. Implementing the recovery in that is not easy. Okay.
Follow up. Mr. Nitin Gadkari, minister in the central government, he had actually last year or something, he said that we are going to collect urine in large quantities from the people and they will purchase also. Like so many liters, so much rupee and all that, and from all the toilets and other places, and then it's going to be our source of cheap nitrogen based fertilizer. And then I heard after some time that they looked at the feasibility and whatever it is, and then finally they have given up on it, at least temporarily.
Okay, my comment will be from theoretical point of view. I wouldn't buy it for nitrogen. I would buy for phosphorus first of all, because phosphorus embedded in urine actually has a value. Because in India, as Indian, as a country, I would say phosphorus is important. I would focus on that first. Secondly, yes, probably what he meant nutrient recovery, which means nitrogen, phosphorus, both. The feasibility could have gone wrong just because of transportation cost. It's nothing. I mean, I have done my own theoretical analysis. Recovering will always be good if you do on site. If you try to run around with a tanker of urine for 20 kilometers, it's not going to be cost effective. Definitely not. Yeah, I mean, again at building level, I mean, it's really not rocket science. If you do in the lab, you realize a very simple and straightforward process. And the moment you install this process, the smell of urine is gone because you are doing precipitation anyway. So it doesn't feel like, bad sort of a nuisance process. So if you install in a building, it will work fine, because the rest is water. Water is fine, water can go anywhere. And even if you are recovering a small amount, this is still something that you are getting out of it. Okay. So you can try at any scale pretty much. But if you try to transport urine, I mean, you can calculate transportation cost. If you calculate transport of urine produced. Sorry. Yeah, it's basically water transportation usually.
Thank you so much.
Something.
In India, we have septic tanks for each house.
Yeah.
We cannot. In that case, it's not feasible, right? Like.
I'm studying in Philippines that topic. I have no answer for that, unfortunately, at this moment. Reason is that septic tanks are not like anaerobic digesters. Anaerobic digesters in this case are designed and maintained in certain way that you achieve complete hydrolysis. So let's say fibers and everything gets hydrolyzed. You have all the release of ammonium and phosphate. Septic tank, it is like a stabilizer rather than an anaerobic reactor. So things get deposited in layers. Okay. And if it's funny old style septic tank, you don't know what is leaching where, so you can't capture your phosphorus because phosphorus probably gone to the nearby groundwater. Okay. So it depends on what is, if your septic tank is a complete bioreactor, if it is lined, if you contain all the nutrients, particularly phosphate, you can apply this concept. But if it is the soak pit, you don't know where is the phosphate, how much is left.
So at apartment level, we can do this.
You can do any level as long as it's not the soak pit. If it is contained, but thing is that those septic tanks people don't build because it's too much of water and they don't know where to go. So unfortunately, the conventional septic tanks are the polluting septic tanks. And phosphate is one of them that goes and leads into the earth. So basically, since you are not containing them, you will not be able to recover effectively.
Because if we let the thing to get transported, again the struvite thing will happen and then the explosion will happen.
There is no explosion fear on that.
If we are transporting the effluent to much more distance from the house to the treatment plant, struvite will be produced in the pipes, right?
If
it closes the pipe, and then the explosion happens when burst pipe just yeah, that's what I mean.
I mean, here I don't think they use that sophisticated pipe, right? It's probably just the nala which carries everything. What I'm suggesting is that if you want to remove the phosphorus, you can remove where it is contained. If your septic tank is differently designed, it contains, which means it has a lining layer, it's not letting phosphate go away. You can recover in-house or you can recover at the sewage treatment plant. It doesn't matter, okay? Wherever this wastewater goes. But the primary problem with the septic tank, household septic tank system, is that they are actually designed to just dissipate water somewhere in the ground. Because there is no way water can go. That's the whole purpose they build a septic tank, because they haven't got connection to the sewer probably. Okay, so first, if you want to apply this concept into the household level or the septic tank type of scenario, you have to ask yourself question where you want to install your reactor. If you want to install reactor at household level, there is no problem. You just have to build a lined septic tank. Okay. And you have to think where the treated water needs to go. Okay, if you can consume the treated water somewhere, then you can apply complete integrated solution in a household. Okay, but if you line it and you don't know where water to throw, then obviously there is no way you can design for it.
Thank you.
Okay, thank you everybody.